In this video, I would like to give an elementary treatment of the 1D wave equation. The derivation of this equation appears in the notes, and I'm not interested in that. I would like to focus on the solutions to this equation. The solutions could be any functions of x and t that satisfy this thing. V here is called the propagation speed. If you think of a wave going through a river or an ocean, then the speed at which the wave moves from point to point is called the propagation speed of the wave. There are many other quantities associated with the wave, like wavelength, etc. We'll come to that soon. A classic example of solutions to this equation from your earlier courses could be the sinusoidal solutions. So y of x comma t could be something like a cosine or sine kx minus omega t, where k is related to what's called the wavelength of the wave and omega is related to what's called the period of the wave, 2 pi over the period t, sometimes also written as 2 pi times the linear frequency of the wave. So let's first of all verify that this satisfies the definition of the wave equation. The partial derivative of y with respect to x, sometimes written yx, is, if we differentiate this, I'm going to get negative a times, I'll pick up the derivative with respect to x only, of sine kx minus omega t. I can add a phase factor phi if I like, but I did not write it for this video. So if I write this in abbreviated form, it's going to be yxx equals 1 over v squared ytt. That's the power of notation. So yxx is going to be negative a times k squared cosine kx minus omega t. But a times cosine kx minus omega t is just y. So that's negative ak squared. Oops, no a anymore. It's just negative k squared y. So that is the left-hand side of the wave equation. Now what about the right-hand side? There you have to take two time derivatives. So let's proceed to do that. Yt, I'm not doing the 1 over v squared yet. So yt is, I'll pull out a negative omega because that's what I get when I differentiate with respect to time. But there's already a negative sign coming from it, cosine becoming sine. So that's going to be plus a omega sine kx minus omega t. And when I take a second derivative, so I'll put semicolons here to separate the two calculations, ytt, this time I'm going to get a negative sign because when I take the derivative with respect to t, that pulls out a minus omega. So minus a omega squared cosine kx minus omega t. Now I put both of these things in the wave equation. So the wave equation gives me minus ak squared cosine kx minus omega t equals 1 over v squared times minus a omega squared cosine kx minus omega t. Cosine kx minus omega t is not always 0. It is sometimes 0, but not always. So those can be cancelled out. Amplitude is never 0, so that can be cancelled out. A is called the amplitude of the wave. I suppose you know these things, but it's worth mentioning. K is called the wave number. Lambda is called the wavelength. Omega is called the angular frequency. F is called the linear frequency. And T is called the period. So a basic course in university physics would have covered these things in the first semester of university physics when you study waves. But it always is worth revising these things. The minus signs also cancel out. So I get k squared equals omega squared by v squared. In other words, I have the propagation speed v, it's just omega over k. It's plus or minus omega over k, which means that this wave can be either going forward or backward. If you have a minus sign, the wave is going forward. Let's study why that is. In our universe, we have the unfortunate property that time always marches forward. How nice it would be if sometimes time runs backwards to correct our mistakes, but that's not how our universe works, or our branch of the multiverse certainly does not have that property of time. Since time always marches forward, negative omega t keeps decreasing. Now the only way kx minus omega t can remain constant, so if you're focusing your vision on a particular point on the wave, let's just draw this point on the wave. So if you're looking at a leaf or something that's on the top of the wave, and you want to see how that leaf is moving, well, as time advances, this part's getting more and more negative. So the only way you can focus your gaze on the leaf is to have kx be more and more positive, because more and more positive minus a bigger quantity has a chance of remaining constant. So this instead, in fact, stands for a wave that's moving to the right with a speed v, because we need x to go on increasing. So with that logic, we choose the plus sign for the propagation speed. Okay. So we have found many interesting things about this wave. You can think of this wave in two separate pictures, because it's pretty hard for you to visualize what y of x comma t looks like. This is a three-dimensional picture. So one way is to think of y in this direction, x in this direction, and t in that direction. Suppose you freeze x. Freezing x is like looking at an ocean wave between two tall buildings in a built-up resort. If you look between two tall buildings, the only indication that there's an ocean there at all, with surf and everything, is the water level goes up and down. So you have simple harmonic oscillation along the t-axis. So if you fix x, you're going to get simple harmonic oscillation along the t-axis. What if you fix time? Fixing time is known as taking a photograph. If you go up on a helicopter and you take the photograph of the ocean, you're fixing time. Then you're going to get the photograph of a wave that looks like that. So if you now let x and t both run wild, you're going to get something that looks like an atomic foam mattress. One of those cheap things. I've lost count of how many of these I've bought over the years to reinforce poorly constructed mattresses that I used to have in my graduate student days. So to get more out of the mattress that was already failing, I used to buy these atomic foam mattresses from Walmart and put them on the regular mattress and then put the bed sheet on it. So it's exactly like the atomic foam mattress, or egg crate foam as it's sometimes called. You should think of one direction of that foam giving you the x, the other direction of that foam giving you t. Now this may lead you to think that only sinusoidal solutions are the solutions to the wave equation. Not so. A great mathematical physicist called Dalham showed that any function f, which is a function of x plus vt, and any function g, that's a function of x minus vt, solves the 1D wave equation. So that's an amazing fact in itself. Let's try to show that it's true. One way to show that it's true is to use a change of variables. Let's do it for f of x plus vt. The proof for g of x minus vt is the same. let u be equal to x plus vt. Then we need to show that it satisfies the wave equation. So need to show that fxx is equal to 1 over v squared ftt. If we do that, we have proved D'Alembert's theorem. Well, at least one half of it. The other half is exactly the same. Let's try to find fx. Fx is the derivative of f with respect to u, f sub u, times ux by the chain rule. The derivative of u, which is x plus vt, with respect to x is just 1. Similarly, fxx is going to be fx of fx. We already know that fx is f sub u. So each time you have fx, you have f sub u. So that's just giving me f sub u squared. Okay, that was easy. Let's now do, I have a feeling I'm doing something weird. It's actually FUU, because that's fx x. So fx x. So it's FUU, not f squared u. So I'll just erase that little mistake there. Some of the dangers in compressed notation is you lose sight of what you're doing sometimes. Okay, now let's do the other one. F sub v, f sub t. Now each time you do t, I'm going to get f sub u ut. But here, derivative of u with respect to t is v. So I get v times fu. Now if I do ftt, this is where it'll really help to write it like that. It's going to be ft, the t of t thereof. Ft itself is v f sub u, the t thereof. The t thereof of anything is v times that function with respect to u. So it's going to be v squared f u. So if you substitute this in the wave equation, you indeed see it satisfied, because the left hand side is fuu and the right hand side is v squared fuu, but that gets divided by v squared, so it's satisfied. In honor of D'Alembert, a three-dimensional wave operator is called the D'Alembertian operator. So in 3D, this wave equation looks a little more complicated. It's del squared. I'm going to use the symbol u as a function of x, y, z, and t. So it is already hard for me to plot the solution to the 1D wave equation, because I needed the y-axis to tell me how big the wave is. That's the up and down of the atomic form matrix, and the x and t directions to give me the remaining two directions. So 3 dimensions are used up in this. Here, to understand this properly, you need to live in 5 dimensions. Well, we are not creatures with that kind of imagination, so we'll just switch to mathematical notation instead. So del squared u over del x squared plus del squared u by del y squared plus del squared u by del z squared is equal to 1 over v squared del squared u by del t squared. Understandably, people got sick of writing this all the time, so they just decided to honor D'Alembert, and they called this the D'Alembertian box operator. The D'Alembertian box is 1 over the gradient, the Laplacian squared, the Laplacian, not Laplacian squared. Laplacian itself is that, minus 1 over v squared del t squared. The Laplacian minus the scaled second derivative of time is called the D'Alembertian wave operator. sometimes called the Dalham box wave operator. So in advanced journals involving Einstein's general relativity and the newly minted gravitational waves, you're going to see equations that look like this all the time. Box U equals 0. You shouldn't wonder what on earth is that. That is the three-dimensional wave equation depicting gravitational waves coming out of a binary coalescence of two neutron stars.